Welcome to the Deep Dive. We're here to sift through your source material and pull out the core insights. Now for, the last 5 years or so, the story in AI has felt pretty straightforward.
Yeah, basically. Go big or go home.
Exactly.
Right.
The path to smarter AI seemed paved with scale. Massive models, trillions of tokens, billions in investment, parameter counts that just sound astronomical. It's always been about brute force.
And look, that approach has definitely given us models that are incredibly fluent. They sound human. But fluency isn't quite the same as, well, actual reasoning, is it?
Mm.
And that's where today's research comes in. It's from Samsung Sale Montreal, and it offers a pretty radical counter-narrative.
Yeah.
They've built this thing called the Tiny Recursive Model, or TRM.
TRM.
And it fundamentally challenges that bigger is better assumption that's driven so much of the field.
So our mission for you today is to really unpack this potential shift. We're looking at a system, and this is the kicker, that has less than 0.01% of the parameters of the big players.
Tiny.
Tiny. And yet, somehow, it's apparently setting new state-of-the-art records on really tough reasoning and logic tasks. So how is this elegant little model seemingly outthinking the giants?
Well, I think to really grasp why TRM is such a big deal, you first have to get why those huge, fluent LLMs sometimes stumble.
Yeah.
They are amazing mimics. They can churn out text that feels completely natural, very human-like. But ask them to do something that needs genuine, multi-step logical thinking, like solving a tricky puzzle or following abstract rules.
That he can fall apart.
They often do. And it's not necessarily that they lack the information.
It's the process.
Exactly right. The fundamental weakness is how they work. Linearly. They generate text one token after another in sequence.
Right.
So imagine the model makes one tiny logical slip-up, maybe a bad assumption, way back at token number 100. Every single token that comes after that is now built on that shaky foundation. That one little error just cascades, dominoes falling.
And the final answer ends up being incoherent or just plain wrong, even if the sentences sound perfect.
Precisely. Even with perfect grammar, the logic is broken.
Okay, so the industry tried to fix this, right?
Yeah.
The main approach seems to be chain of thought prompting, COT. Can you walk us through that? And why isn't it a complete solution?
Sure. COT is, well, it's basically an external instruction. You tell the model, hey, think step by step or show your work before you give the final answer.
Like making it write out its reasoning.
Yeah, it forces the model to try and make its internal thought process visible as text. And look, it helps. It does mitigate the problem somewhat, but it doesn't fix the core architectural issue, the linearity.
Yeah.
And it comes with its own baggage.
Okay, like what? What's the cost?
It's a huge cost, actually. First off, it's computationally very expensive. You're generating way more text, this long, detailed draft, every single time you ask a question.
More processing, more time.
And second, you need these enormous, very specific data sets just for reasoning tasks. They're incredibly difficult and time-consuming to create and clean up. You have to teach the model how to perform this external step-by-step thinking.
So it's data hungry.
Very. And even after all that effort, the structure it outputs is still linear text. So it's still vulnerable to those kinds of logical errors, just like a human drafting an argument might be. Logical consistency is still a challenge.
So we've got this picture of somewhat brittle giant models being patched up with these expensive data-hungry external methods.
That's a fair summary.
Okay, now let's bring in the challenger. The Tiny Recursive Model, TRM, developed by Samsung researcher Alexia Jolicoeur-Martineau. Let's just start with the size again, because 7 million parameters, that just sounds wrong compared to billions.
It sounds wrong, but it's right. Just 7 million parameters. And you said it, the big models are in the hundreds of billions, some even pushing trillions. TRM is genuinely less than 0.01% of that scale.
Wow.
If you think about the current AI landscape as this massive resource race, TRM is it's a totally different philosophy. It's about efficiency.
But, okay, skepticism kicks in here. If a model is that small, how does it avoid just forgetting everything or overfitting massively on these very specific reasoning tasks? How can 7 million parameters hold enough information to solve complex logic problems?
And that's the crucial question. The answer isn't in size, it's in the design. It's about smart architecture and, critically, recursion, rather than just brute force scaling.
Recursion.
Now, TRM isn't entirely out of the blue. It builds on an earlier concept, the hierarchical reasoning model, HRM. But it simplifies HRM significantly.
How is HRM different?
HRM was more complex. It actually used 2 separate neural networks, kind of inspired by different brain regions designed to check each other's work.
Interesting. That sounds complicated.
It was. TRM streamlines all that. It uses just a single compact network specifically designed to refine its own thinking internally. No need for two separate checkers.
Okay, let's unpack this. You said chain of thought is like writing an external draft. What does TRM's internal recursive thinking actually look like? How does it self-correct?
Right. It's a fundamental shift. Instead of that public step-by-step rating, think of it more like a private, continuous self-editing process happening inside the model.
Okay.
The mechanism has basically 4 key parts that operate in this tight, closed loop.
Tell us about the loop. What are the steps?
Okay, first, the model gets the problem, or the question, as usual. But crucially, it also gets 2 internal things. Its own first guess at the answer and something called an internal reasoning state.
Internal reasoning state, like a private scratch pad.
Exactly. That's a great way to put it. It's a mental workspace only the model sees, completely unlike the public text generated by Coty.
Got it. So it's not starting fresh each time. It's immediately looking at its current thinking. What's step 2?
Step 2. Using the question, its current guess, and that internal state, the model works to refine its reasoning step by step, but internally.
Okay, still private.
Still private. Third, based on that refined internal reasoning, it updates its answer guess.
Makes sense. And the recursion part?
That's step 4. The newly refined answer guess and the updated internal reasoning state are immediately fed back into the start of the loop. Step 1 again, but with better inputs.
Ah, so it cycles. It keeps tightening its own logic.
Precisely. It can loop like this up to 16 times for a single problem. It's like having an internal debate with itself, where the network critiques its own logic and progressively improves the answer.
And because that whole reasoning process, that scratch pad, is private.
It avoids that linear cascade of errors we talked about with the big models. An internal mistake can be caught and corrected in the next loop rather than derailing the entire output.
Fascinating. So what does this different structure, this recursive loop, mean for actually training the model? The source mentioned it avoids some complex math.
It does, and that's a huge practical advantage. The older model, HRM, because it had those 2 interacting networks, had to rely on some pretty heavy theoretical math, things like fixed-point theorems, just to mathematically prove that the 2 networks would eventually agree on the right answer.
Which sounds brittle, restrictive.
Exactly. It made development harder. TRM, because it's just one network looping, is much simpler. It can be trained using standard backpropagation, applied through the whole recursive process.
Meaning it's easier to work with.
Much easier to optimize, way more flexible. You don't need those complex mathematical guarantees for it to function effectively. And interestingly, they found something else surprising during development. A simpler 2-layer TRM actually performed better than deeper versions they tested.
Really? Less complex was better.
It suggests the smaller model was less likely to overfit the training data, especially since these specialized reasoning datasets aren't always huge. Sometimes less complexity really is an advantage.
Okay, this architecture sounds really elegant, really clever. But theory is one thing. The real test is performance. Did this tiny 7 million parameter model actually deliver against the giants in the benchmarks?
Oh, it delivered. The results are quite dramatic, actually. Take Sudoku Extreme. That's a pure test of logic and constraint following. The older HRM model got about 56.5% accuracy, TRM. It jumped all the way up to 87.4%, almost perfect.
Wow, that's a massive leap just from changing the architecture.
Huge. And similarly, on another tough one, Maze Hard, TRM scored 85.3%. Again, a big jump from HRM's 74.5%.
Okay, strong gains on logic puzzles. But what about the benchmark that everyone points to for, real intelligence? The ARC-AGI, the Abstract Reasoning Corpus.
Ah, yes, ARC-AGI. That's the crucial one.
Because it's not about language, right? It's designed to test fluid intelligence, pattern recognition.
Exactly. It often involves looking at abstract visual patterns and figuring out the underlying rule or transformation. It's supposed to measure genuine reasoning ability, not just language mimicry or recalling facts. It's a much harder test of generalization.
So the $1 million or maybe the 7 million parameter question, how did TRM do against the multi-billion parameter behemoths on that test?
Okay, so on the first ARC-AGI benchmark set, ARC-AGI 1, TRM achieved 44.6% accuracy, which is respectable. But the real eyebrow raiser is the harder set, ARC-AGI 2. There, TRM scored 7.8% accuracy.
Now, hang on. 7.8% sounds low in absolute terms.
It does, until you put it into context. Context is absolutely everything here.
That's the context. How did the big guys do?
This is the punchline of the research, really. That 7.8% on ARC-AGI-2 achieved by the 7 million parameter TRM is actually better than what some much larger models achieve. For instance, a system like Gemini 2.5 Pro reportedly scored only 4.9% on that exact same benchmark.
Wait, seriously? The tiny model beat the giant one on this core reasoning test.
By a noticeable margin, it shows TRM isn't just parameter efficient, it seems to be genuinely better, or at least competitive, at complex abstract reasoning compared to a model thousands of times larger.
That's pretty stunning. So the smart recursive architecture isn't just saving parameters, it's leading to better results.
It appears so, and this leads to operational advantages too. We talked about size, but TRM is also designed to be fast and efficient to run.
Smarter training, smarter operation. How does that work?
Well, they integrated a clever technique called adaptive computation time, or ACT.
ACT. Adaptive computation time. What does that do?
It basically lets the model decide for itself how many of those recursive loops it needs to run for a given problem. If it solves it quickly, it stops early. If it's a tough problem, it keeps iterating.
So it dynamically adjusts its thinking time. That sounds like a sensible optimization for speed. But doesn't adding that kind of decision-making layer usually add its own computational cost?
Right.
Doesn't the model have to spend extra effort figuring out when to stop?
That's the standard trade-off, yes. Normally, implementing ACT requires an extra forward pass through the network on each step, just to calculate the probability of stopping. It adds overhead.
Okay.
But here's another really neat part of the TRM implementation. They managed to get rid of that extra forward pass.
How do you skip the step where it decides to stop?
They integrated the stopping calculation directly into the main computational pass of the network. It's a technical simplification, but the upshot is they get the benefits of ACT, the adaptive thinking time, without the usual computational penalty.
Wow. So it's efficient in its core logic and efficient in how it decides when it's done thinking.
Exactly. Ultra-low computational cost combined with superior reasoning.
Okay, let's pull back and think about the bigger picture here. What does all this mean for you, the listener? For the future of AI beyond the research labs? If smart architecture really can beat raw scale, what are the implications?
I think they're potentially huge, really falling into two main categories. First is sustainability.
Right, less computation.
Means drastically less energy consumption. We might be able to achieve really advanced AI reasoning without needing these planet-scale data centers and the massive environmental footprint that comes with them.
Maybe the end of the melt a glacier to train your model era.
We can certainly hope. The second major implication is, I think, democratization.
How so?
Well, when a powerful reasoning system is this small and this efficient, it opens the door to running it directly on everyday devices. Think your smartphone, your laptop, maybe future smart glasses or wearables.
Instead of needing a constant connection back to a giant server farm.
Precisely. It could put advanced AI capabilities directly into people's hands, locally, without relying on massive, centralized, expensive infrastructure. It lowers the barrier to entry for innovation everywhere.
So the core message here, really hammered home by TRM, seems to be that AI progress doesn't have to mean just endlessly scaling up, consuming more resources.
No, it suggests the focus should perhaps shift more towards the quality of the computation, the intelligence of the architecture, learning to reason, to check yourself, to self-correct efficiently within a compact system that might be the more fruitful path towards more general intelligence.
It really feels like TRM is proving that depth of thought, that recursive refinement, can genuinely outperform brute force. Elegance in design trumping sheer size.
It certainly makes a strong case for it. Which kind of leaves you, the listener, with a final thought to chew on.
Go on.
If perhaps the most exciting innovation in AI right now stems from thinking smaller, from applying this elegant, recursive, self-correcting logic, what complex problem in your own world, maybe in your business, your research, even just managing complexity in your life, is currently being tackled with sheer brute force? Could that problem, whatever it is, be unlocked or radically simplified not by adding more resources, but by finding a smarter, more elegant, maybe even tiny self-correcting structure to handle it? Maybe thinking smaller is the key to the next truly smart solution.